So in this lesson, I introduced the last important piece that you need to know to understand how to interpret an NMR spectrum, namely spin-spin splitting. So let's look back at the NMR spectrum of ethyl bromide, the one that I first introduced this topic with. Based on our previous lesson, it should now be obvious why the peak for the A hydrogens is at 3.4 and the peak for the B hydrogens is at 1.6. The A hydrogens being closer to the electronegative bromine than the B hydrogens are, and they're in the right region according to the chart that you're going to need to be able to use to solve these sorts of problems. Now we must consider why the peak for the A hydrogens is split into 4 lines and the peak for the B hydrogens is split into 3 lines. So to solve this, to understand this, we have to look at the nuclear spins of the hydrogens on the adjacent carbons. So the exact resonance frequency of HA in a particular molecule depends on the spin states of the B hydrogens. So in this case, if we're looking at A, there is one adjacent carbon, and that carbon has 3 hydrogen atoms of type B. There are 4 combinations of the spin states of those 3 hydrogens. They could all be spin up. You can have 2 spin up and 1 spin down, and if you look at this, there are 3 different ways that that can happen. You can have 2 spin down and 1 spin up. Again, 3 different ways that that can happen. Or all 3 of them can be spin down. If all 3 HBs are spin down, the peak for HA is slightly upfield or to the right. If all 3 HBs are spin up, the peak for HA is slightly downfield or to the left. And I'm not going to derive why this is the case. That is upper level physical chemistry. But since we are looking at many molecules in a sample, we will see all of the possible combinations for HB reflected in the peak for HA. In other words, there will be some molecules where they're all up, some molecules where they're all down, some molecules where there's 2 up, 1 down, some molecules where there's 2 down and 1 up. Statistically speaking, the middle 2 arrangements, 2 up and 1 down or 2 down and 1 up, are 3 times as likely as either all 3 being up or all 3 being down. That's what I'm trying to indicate with this green diagram here. So these peaks then will have 3 times the intensity, because there will be simply more molecules in solution where your HBs have 2 one way and 1 the other way than molecules in the solution where all of the HBs will be either up or down. So as a result of this, HA appears as a quartet, and the relative intensities of the 4 lines in the quartet are 1 to 3 to 3 to 1. And that's exactly what we see in the spectrum of ethyl bromide. Okay, what about HB? Well, if you're looking at HB, there is 1 adjacent carbon, the one that contains the HAs, with 2 hydrogen atoms, the 2 HA hydrogens. So when you have 2 hydrogen atoms, there are 3 possible combinations of the spins of those 2 hydrogen atoms. They're either both up, 1 up and 1 down, or they're both down. Okay, so if both HAs are spin down, once again, the peak for HB is slightly upfield or to your right. If both HAs are spin up, the peak for HB is slightly downfield or to your left. And again, statistically speaking, the middle arrangement is twice as likely. There are 2 different ways in which you can have 1 up and 1 down. So therefore, this peak has twice the intensity, giving us a 1 to 2 to 1 triplet. 3 lines triplet in a 1 to 2 to 1 ratio. Okay, so generalizing this example leads us to what we call the n+1 rule. And the n+1 rule, and I put this in red because it's really important, states that the number of lines that a peak is split into equals the number of hydrogens on adjacent carbons plus 1. Okay, so when we were looking at HA, there were 3 hydrogens on the carbon that we called HB, and therefore the peak for HA was split into 4 lines. 3 plus 1 equals 4. When we're looking at HB, there are 2 hydrogens of type A, 2 plus 1 equals 3, and HB is split into 3 lines or a triplet. Another important piece of the n+1 rule that we're going to consider on the next slide is the statement in italics here that only hydrogens that are inequivalent to the hydrogen being observed cause splitting. And I will get to that shortly. But before I get to that, I want to give you the terminologies and the relative peak intensities, at least through septets. Okay, so if you have a single peak, a single line, we call that a singlet, and we say that it has full intensity. If you have 2 lines, we call it a doublet, and in order to be a doublet, those 2 lines have to be in approximately equal intensity. That's when you have 1 hydrogen on the adjacent carbon. You get a singlet if you have no hydrogens on the adjacent carbon. So a doublet is when you have 1 hydrogen on the adjacent carbon, and the 2 lines are in a 1-to-1 ratio. If you have 3 lines due to 2 hydrogens on the adjacent carbons, then we call it a triplet, and as we saw, the intensity ratio is 1 to 3 to 1. 4 lines due to 3 hydrogens on the adjacent carbons, call it a quartet, and as we saw in the last slide, the ratio is 1 to 3 to 3 to 1. 5 lines, that means if you have 4 hydrogens on the adjacent carbons, and there have to be 2 carbons in this, at least 2 carbons in this case, because you can't have 4 hydrogens on 1 adjacent carbon, or else carbon would form 5 bonds. So if you have 5 lines, then we call it a quintet, and the intensity ratio is 1 to 4 to 6 to 4 to 1. 6 lines is a sextet, 1 to 5 to 10 to 10 to 5 to 1, and 7 lines is a septet, 1 to 6 to 15 to 20 to 15 to 6 to 1. Now, you may wonder where we get all of these ratios from, and if you look at it carefully, especially the way I have it drawn here as a triangle, the intensity ratios correspond to the terms in Pascal's triangle, which is something you may have seen previously in a math class and never thought it would actually be useful for anything. Well, this is where it's useful for something. So to get the intensity of a particular line, you simply take the 2 terms that are slightly above and to the left and slightly above and to the right of it on the triangle and add them together. Okay, so for the intensity of the central line in a triplet, you just add 1 plus 1, those are the 2 intensities above it, to get 2. For the central line in a quintet, the 2 numbers above it in the triangle are 3 and 3. You add those together and you get 6. For the 3rd line of a sextet, you're adding together 4 and 6, the 2 numbers above that position, and getting 10. Okay, a few more thoughts. First of all, I would like to show you a picture of what these peaks actually look like in a spectrum, so you get a sense of seeing what they really are. So we've already seen examples of triplets and quartets. I think you could imagine singlets and doublets pretty easily. But quintets, sextets, and especially septets, look at that septet there. There's going to be a very common arrangement, namely an isopropyl fragment, where you're going to see septets. But look at how small those end lines are compared to all the rest of the lines. In some cases, you will have to look really carefully at the spectrum in order to be able to actually make out those 2 end lines. And that's why sometimes when we show you the spectrum, the individual peaks are blown up above the spectrum itself so that you can see all the lines that make up those peaks. Okay, secondly, I promised you I would get back to what I mean by only hydrogens that are inequivalent to the hydrogen being observed cause splitting. Well, what I mean by that is if you consider ethane, which of course has 2 carbons and 6 hydrogens, if you go take an NMR spectrum of ethane, which wouldn't be the easiest thing in the world to do because ethane is a gas, but suppose you can take an NMR spectrum, it will be a singlet because all 6 hydrogens on the 2 carbons are equivalent. When we say that hydrogens are inequivalent, we're saying that they're a different distance away from a functional group or an electronegative element. There are no functional groups in ethane. So its NMR spectrum is a singlet. If, as opposed to being, if you applied the n+1 rule strictly, you would say for one particular hydrogen, there are 3 hydrogens on the adjacent carbon, and you would think it might be a quartet. It is not. It is a singlet. The same thing applies to benzene. Benzene is a singlet because all 6 hydrogens on the 6 carbons are equivalent. There's no functional groups on the ring. Once we get to aromatic compounds that have additional functionality on the ring, things get a little more complex, and we'll have an entire lesson dedicated to dealing with those situations. Another rule is that splitting is usually not observed to hydrogens on oxygen or nitrogen. That's why when I gave you the n+1 rule, I said the number of hydrogens on adjacent carbons. So the NMR spectrum of methanol is 2 singlets instead of a doublet and a quartet. Okay, there are very occasional cases which may show up in a problem here or there where you do see the splitting to hydrogens on an oxygen. That has to do with the exact conditions under which the spectrum were recorded. If that is the case, I will make it very clear to you in the problem. And then finally, there are a few complex cases, especially when we're dealing with aromatic rings, but there's actually even more complex cases than that, where the n+1 rule is not obeyed. Most of the cases where the n+1 rule is not obeyed are way beyond the scope of this course, and they're things that we might consider in 300 level chemistry courses or even in graduate level chemistry courses. For this introduction to NMR, I am almost always going to only restrict our discussion to molecules where the n+1 rule is obeyed. I said almost always because we will see one important exception, and that involves compounds that contain aromatic rings, which we're going to look at in a future lesson. However, before we get to a lesson involving aromatic rings, in the next lesson I want to summarize my approach for how you approach an NMR problem. Okay, so we'll do that in the next lesson.